Hi, Abhay, good morning.
Good morning.
Did we do a potential divide? We did, no? The applications also we did, right?
Yeah.
So did we do this question? Yeah, right.
Mm, where is that question?
Explain how the potential of wire changes with its length. Yeah, we did. We remember
Yeah.
we did this application too. We
Yeah.
rich,
Yeah.
and then we
That
have
means
to
this
start electric tensor circuits,
sensor.
or do
Yes, sensor.
we have to start this, right?
Yeah.
Right. Now, as we learned about the potential dividers, we can use the potential dividers in these sort of applications. Now, the first thing we learned about is the Wheaton bridge. Now we are learning how the potential divider is applied in electric sensor circuits. So
Yeah.
we have two types of sensor circuits that we need to analyze. One is the temperature sensor circuit, and the other one is the light sensor. Mm. So a temperature sensor circuits have the thermistor connected series with another fixed resistor,
Yeah.
and light sensor circuit is connected with a LDR with another fixed resistor. Right. So first we will look at electric sensor circuit, that is temperature sensor circuits. Right. Now we know in a thermistor we call a thermistor as a negative temperature constant device. That means as the temperature increases, resistance decreases. I hope you remember how
Yeah.
the temperature and resistance are related in a semiconductor. Remember,
Yeah.
the temperature is increasing, the charge density increases, it
Yeah.
increases the current. If the potential difference is constant, that
Yeah.
increases the resistance. Or in other way, if you use the band theory, if you increase the temperature, that means energy from the radiation by heat is absorbed by a lot of valence electrons, and a lot of valence electrons goes to the conduction band, so that the current increases, so that also reduces. Hmm? Right.
Yeah.
Let's look at this circuit. If you look at this circuit, if you look at the energy conservation, now Vs means they will have a power supply connected across these two, the supply voltage. Now, potential difference through this resistor, let's say V, and the potential difference through the thermistor, let's say Vt. So what we can say about these two, V and Vt, they add up to the supply. Yeah. So when RT, when the temperature of the surrounding, let's say it's reduced, when the temperature is reduced, means the
Yeah.
temperature is reduced, let's say, what happens to the resistance of the thermistor? It increases,
Then.
right?
Yeah.
Uh, Surrounding reduces, the resistance of the thermistor increases, and remember, potential divider principle states that potential difference across each resistor is divided in terms of the ratio of resistors. Remember? So therefore,
Yeah.
resistance increases means the VT value increases. So therefore, according to
Yeah.
potential divider principle, the value of VT should be increased. Now,
Yeah.
value VT increases means, but what about the value V?
That should decrease.
Yeah, that should decrease, right? Vt and V are adding up to a constant value, which is the supply. Right. Now tell me, we want to, now in a cool condition, what we need is a warming mechanism, right? A heater, rather. So where do you think of connecting the heater circuit? Is it across the fixed resistor or is it across the thermistor?
Your voice, like it just sometimes it goes and it comes. Like, are you using a mic? Like,
Yeah,
it's
I think.
sometimes it's like far. It's like far away. Like you're talking. Sometimes far away.
Okay, now can you hear me?
Sometimes it comes, then it goes.
I think
Uh,
it's your headphone. Are you wearing headphone?
no, I'm not wearing it.
That's why you should wear a headphone then. Your speakers have a problem, I think. Last time also, remember?
Right, hold on. I'll put that.
Found the headphone. Did you find the headphone? Are you set up?
Okay, I turned on I put the headphones now.
Okay. Now can you hear me now properly?
Right. I'll tell if it's like very
Yeah.
quiet.
I think it was your speakers. Now I cannot hear the background noise also. I think it's better now. Hmm?
Ah,
Right. So the resistance of the thermist increases. I said the share of potential difference across that also increases. Now, say that you have a heating circuit. For a heating circuits to work, say it needs like these arbitrary values, 10 volts. Now,
yeah,
supply is given is like 20 volts, let's say.
yeah,
Now, we learned that the resistance of the thermistor increases, right? When the
yeah,
resistance of the thermistor increases, the potential difference across that is also increasing. Now,
yeah,
let's say the resistance of the thermistor arbitrarily, like assume the resistance of the thermistor at the beginning was zero,
yeah,
not zero, like, yeah, let's say it's zero. It is like the temperature is high, the resistance is zero. So, what about the potential difference across the thermistor?
it's
That's also
very
zero.
low.
Zero,
It's
like
zero.
very, very close to zero. Now, as the temperature cools down, what happens? Resistance increases. So
Yeah,
when the resistance increases, what happens to that potential difference?
it
It
increases.
also increases. So at 5 volts, what happens? If I have connected the heating mechanism across the thermistor, it will
Then,
trigger. It
yeah.
will trigger and it will turn on. Am I clear?
Okay. Yeah.
So
So
therefore,
R is the heater. R.
no, no, no. R is a fixed resistor. So where do we connect it across is like this. Now we connect the external part like this, the heating circuit like this. So heating circuit is here. This is the heating circuit. For
So
heating
that
circuit
has a
to work,
voltmeter.
not the voltmeter. So heating circuit needs a power. So heater is connected here.
Okay.
So heater works only when it has a 5 volts through it. Now, when the voltage across the thermistor is 0 volts, heater doesn't work. When the voltage across this like 2 volts, it doesn't work. When the heat resistance potential thermistor potential difference only becomes 5 volts, this will start work.
Uh,
Okay. Huh?
yeah.
So using the potential divider, I can distinguish which voltage this works, and the triggering part can be done. That's why we say sensing. It works according to the temperature. Am I
Uh,
clear?
uh,
Yeah.
yeah. So the heater will, what if it's above 5? Like,
Pardon?
if it's above 5 years,
Yeah, it will work. Above 5 volts, it will work. It's like
uh,
almost 5, it will work. So what we need is to start the heater, because if it is below 5 volts, that doesn't mean that means that we don't need the heater at that temperatures. Only
yeah,
when it goes below a certain temperature, we need the heating circuits to be working. Hmm? So that the separate circuit is connected across that two ends. Yeah.
Yeah.
Right now, similarly, say that I need these circuits to work for a, now this is for a heating circuit. So I need these circuits to be working for a air conditioning system. Where should I connect the air conditioner? Is it across the
Across,
fixed resistor or thermistor? Air conditioner should be connected.
is it across R, the fixed one?
The first one. Why? So as the temperature goes up, that means the graph will go this way. Then I'll draw an arrow. The temperature rises. What happens to the thermistor resistance? Thermistor
Yeah.
resistance reduces. Yeah. Thermistor reduces, resistance reduces means thermistor voltage reduces.
The
What about
voltage
fixed
across
resistor? Yeah,
R
fixed
will
resistor
increase.
potential difference. Yeah, fixed resistors potential difference increases. So to trigger the AC system, we should connect it across the fixed resistor. Yeah, am I clear?
Yeah, yeah,
So now do you understand why do you have a fixed resistor and a thermistor?
yeah,
Huh? Mm.
yeah,
So according to our taste, we can connect.
yeah,
Similarly, if this to work in a higher temperatures, as a cooling mechanism can be connected across the fixed resistor. Am I clear?
yeah,
All right. So let's write this down, shall we?
yeah.
Draw the circuit diagram on the right hand side of the book and the writing part on the left hand side. I think you
Okay.
have enough space, yeah?
Yeah.
So just sketch this one also, how the resistance
Ah,
and
yeah,
temperature works.
yeah,
This is something that you have done in IGCSE. Remember
yeah.
the graph? But anyway, we will draw it up here as well. Today we'll try to finish the theory. Yeah?
Ah, yeah. What is that? What's
Theta,
on the x-axis label?
theta, temperature,
That's T.
theta.
Theta. Ah, T.
You know theta, right?
Yeah, yeah.
I was drawing it using a mouse. That's why it's like this theta.
Ah, theta is used to represent temperature.
In like usually yes, but sometimes theta is used to represent angles also, isn't it?
Yeah, yeah.
Now, similarly, can you guess what happens in light sensor circuits?
Light sensor circuit. Is it the same circuit diagram?
Yeah. So what we do, we replace the thermistor with.
Light dependent circuit.
Hmm. Now, have you seen the street lamps in like they turn themselves automatically during dark and they
Yeah,
go off during the daytime? So earlier days there were people assigned to do that, but
yeah,
nowadays that happens automatically. Hmm?
yeah.
Now, can you guess what happens in the light sensing circuits?
Mm, mm.
Okay, first write this down. Are we done writing?
I'm on last.
Okay.
Mm, yeah, that.
Right now, help me out here. So light intensity reduces. What happens to the resistance of the LDR?
Increase.
It increases. So now this is the circuit. Now can you try and guess what happens in light sensing circuit when light intensity reduces?
As light intensity reduces, the resistance of LDR increases. Then it should be connected to the fixed resistor.
No,
Delta.
no, because the resistance increases. No? So resistance increases means the potential difference across that also increases.
Ah,
So we should connect the bulb across what?
the LDR.
LDR. See, nothing big, right?
Yeah.
So LDR resistance increases with the light intensity is reduced. So according to the potential divider principle, the resistance across the LDR is more compared to the potential difference across the fixed. So to street lamps usually they connect across the LDR to work in dark conditions like this.
Then to turn it off.
Huh?
Then to turn it off like in the daytime.
Sorry, there is
To
a
turn it off in the daytime.
yeah, now as the that becomes more intense, what
Yeah.
happens?
The resistance.
Resistance drops. Resistance drops means potential drops. So it automatically turns off.
Ah,
Huh? Do you understand?
yeah. Right.
Huh? Does that make sense?
Yeah.
Simple, right?
Yeah.
Here the street I spelled wrong, I think. Is it STREET or EAT?
It's double.
Ah, double A. Sorry. See how important the potential divider principle is. Huh?
Yeah.
So if we use this potential divider method, now we used it for a variable resistor. We used it as a way of increasing the potential difference from 0 to a maximum value. And we used to find the unknown resistance using that. And then
Yeah.
now we are using it in sensor circuits. Hmm?
Yeah.
After that, there is a question on the other side. Do it, huh?
Yeah.
Do it and send it to me. Huh?
Yeah.
Just a picture. Can I change the screen?
I'm doing the question. I turn to the question.
Okay,
Sorry,
so can
what?
I change it to the question?
Oh, yeah, yeah.
This one. The circuit diagram below shows a 6 volts battery of negligible internal resistance connected in series to a light dependent resistor LDR, a variable resistor, and a fixed resistor R. For a particular light intensity, the resistance of the LDR is 50 kilo ohms. The resistance of R is 5 kilo ohms, and the variable resistor is set to a value of 35 kilo ohms. Calculate the current in the circuit. Calculate the reading on the voltmeter. State and explain what happens to the reading on the voltmeter if the intensity of the light incident on the LDR increases. For a certain application at a particular light intensity, the potential difference across R needs to be 0.75 volts. The resistance of the LDR at this intensity is 5 kilo ohms. Calculate the required resistance of the variable resistor in this situation. The first part is fine, right? So calculating the current.
Yeah.
So total resistance is found. What is the total resistance?
Mm,
55 and 35. That is altogether
and,
90 kilo ohms, isn't it?
yeah,
So we can find the current. V equals IR. Yeah.
yeah.
What is it?
I say the
So R.
uh,
This
the
much answer you get. See if you get this answer.
the
So total current is 6.7
six
into 10
points.
to the power minus 5 amperes, isn't it?
Yeah,
Yeah.
yeah,
So now you can find the potential difference, or sorry, the voltmeter on the voltmeter reading. You can find just multiply this current value by the resistance.
yeah.
Right?
Across R. No? Yeah,
Yeah. Or else you could use the potential divider method. But since we have the current here, we just multiply it by the resistance. So we get the voltmeter reading directly. Yeah.
yeah.
Part B is the difficult part. State and explain what happens to the reading on the voltmeter if the intensity of the light incident on the LDR increases.
Hold on.
Yeah.
One second. Simplify minus 0.334. So, part B. State and explain what happens to the reading and the voltage. The intensity of light incident on LDR. So, when light incident on LDR increases, the
Hmm?
resistance across LDR will reduce. So
Hmm.
then the resistance of the LDR reduces, so the voltage drop across that reduces. So then
Hmm.
volt reading will increase.
Yeah. So the voltmeter is not connected across the LDR. It is
Yeah,
connected across the fixed
that
resistor.
is so.
Yeah. So light intensity increases means the resistance across the LDR
LDR.
reduces. So that reduces the potential difference. So however, the all these potential differences are adds up to 6 volts. That
Yeah,
means across the other two, it should increase
yeah,
to compensate the reduction. Yeah.
yeah.
All right. So let's write this answer properly. If the light intensity of the LDR increases, if the light intensity on the LDR
LDR, LDR
increases,
increases.
its resistance decreases.
resistance
Its resistance decreases.
decrease.
So there will be a smaller potential difference across it. So there will be a smaller potential difference across it. There will be a smaller potential difference across it. So there will be a smaller potential difference across it. However,
Sir,
yeah,
can you increase your mic volume because these headphones are a bit like soft, the volume.
mm, I am speaking now. Can you hear me?
Yeah, can hear, but it's like volume is less. Yeah.
I am using the maximum volume.
And like go your mic, you can see on the
Yeah,
screen the
yeah.
mic,
Wait, I'm going there.
the little arrow
Mm, I'm actually using the maximum volume.
of the mic.
Mm,
Okay.
yeah, because wait. Uh, yeah, I have been using the maximum. Yeah,
Okay.
right. This last this session I didn't have any issue. So yeah, if you want me to speak in higher tone, yes, I can. But can you hear me now? If I speak in this voice,
Yeah, okay. I just had maybe like press the earphone
or
little bit.
however, the question is about the voltmeter. However, the question is about the voltmeter, which is across a different component, which is across a different
Cross different
component.
compound.
As the EMF of the battery is shared, as the EMF of the battery is shared,
Yeah. Uh,
out all out across all the resistance, as the EMF of the battery is shared out across all the resistance. If the potential difference across the component decreases, if the potential difference across one component decreases, if the potential difference across one component decreases, there must be a greater proportion used up. There must be a greater proportion used up over the other two, over the other two. So the reading on the voltmeter will increase. So the
okay.
reading on the voltmeter increase.
Right.
Okay, done. Now what about the next one?
For a certain application at a particular light intensity, the potential difference across R needs to be 0.75 volts. The resistance of the LDR at this intensity is 5
5
kilo
kilo.
ohms. Calculate the required resistance of the variable resistor in this of the variable resistor in this situation. Right.
Use the potential divider method. Don't
Yeah.
use current method.
Okay.
Now at a certain application, they say LDR, no,
Ah,
R cross, you have, what is the potential difference? 0.75.
shall I try?
Yeah, yeah, I'm just writing the data on the tape
Ah,
screen. So potential difference across this is 0.75 volts. And the resistance of the LDR at this intensity is 5 kilo ohms. This one is 5K. Yeah. Mm, what is the other one's resistance?
The which one? The area.
No, the variable. We need to find the
That's
variable, right?
yeah. We have time there.
So let's call it R dash.
Five
We need to find R
into
dash. We know R, right? What is R?
R is 5K.
It is said in the beginning, no?
Yeah. Mm,
Is my data correct?
Data
Correct, no?
5K.
We need to find this.
Yeah, yeah. 5. I get as 30 kilo.
30K.
30 kilo.
No, let's see. I think you're correct. Now using the potential divider thing, so R is 5K and variable resistor we need to find. LDR also 5K. Yeah. So potential difference across R is 0.75. So we can consider the LDR and R to be in series. So we apply the potential divider principle to R, this one. So that gives us potential difference across is 0.75. Resistance across it is 5K. The total resistance is 5K plus 5K plus X, that is the R dash, times 6. So when you do this, your answer will be in kilo ohms 30.
Yeah.
Yeah. Understood?
Yeah. Yeah.
Can I erase this?
Yeah.
Is it difficult?
No.
Right. Now there are some questions. Can we do them? And in one of these questions, there's a small printing mistake. I think question number 3. Question number 3. It says the fixed resistor R has a resistance of 100. It is printed. It should be 1000. Huh?
5.
This one here. Can you
Ah,
see?
yeah. Sure. Can I fix the version?
Yeah.
that.
Right, continue. Hmm?
Yeah.
What's the current for the first one?
Almost 4.24,
We need the resistance, right?
yeah,
For that.
and the current is 8.61. That
Hmm.
A1.
Milliamperes. Hmm?
Yeah.
What is the R?
Uh,
You should have found the R and found this.
R I found, yeah, R 475.
Ah, ah. So how do we get it? We know the voltmeter reading is 4.1. That
Yeah,
means across 220, it will be 4.1 minus 6. So then we
yeah.
can use the potential divider principle. Simply uh, R2 220 is equal to 4.1 over what is the potential difference across 220 is 1.9. Yeah.
Yeah.
So when you solve this ratio, we get R as 479, 75. So
79.
75, 75.
Okay.
That can be used in the total resistance of 1, and we can find the current as 8.6 milliamperes. Yeah.
Yeah. Oh, in third. Mm,
What is the answer for 2?
Answer for
A,
3A.
3A, 3A.
And just that.
Ah, carefully do it. So first one, if I just read it out for a second, the LDR is used in the light sensing circuit shown in the following figure. In bright light conditions, the resistance of the LDR is 200 ohms. The fixed resistor R has a resistance of 1000 ohms. The cells have negligible internal resistance. There you have to correct it as 1000. Huh?
Yeah.
Show that the reading on the high resistance voltmeter, resistance of 1 mega ohm, in bright conditions about 4 volts. Now there we don't really consider the voltmeters resistance. We can, because they are like high resistance voltmeter, so we
Yeah.
don't really. Okay, do it by yourself. Then we'll discuss.
Yeah.
Once you do, can you send me a picture of it
Yeah. Okay.
working? Okay, the first one is correct. Abe, don't take much. Don't think much. Okay, it's easy. Take it easy. Like, so think in terms of ratios. Okay, so then it's easy. Don't always stick to the potential divider principle. So the total resistance, how much fraction of resistance is across the voltmeter. That's all you need to think. Huh?
Yeah, yeah.
Okay, that's correct. That's correct. Then next one.
Okay, remain. So for this one, it's the voltmeter resistance we are reducing it from 1 mega ohm to 2000. Then
Yeah.
by
So
doing
you
that,
can't
some,
neglect.
yeah.
Yeah, you can't neglect the voltmeter resistance. So
So that
recall
means,
when we did first we like in the first stages when we did what do you call the potential dividers. Let me show you without saying the answer. I will show you a small hint. Huh?
yeah.
Here we did a question like this. Can you remember? Yeah, here. This one. How did you find the potential difference across this section?
We used to combine this.
Hmm. You understand?
Uh, um,
You need to take the combined resistance. No?
um, uh, so that will like I can use that for the calculation like RC.
Yeah, you
Uh,
can. You have to use. Last time we used it. Can you remember?
yeah,
Now, listen. Hmm? Now that means voltmeter resistance cannot be neglected because it has a certain resistance that is there like 2000 and R is like 1000. That means if you have a certain potential difference across this, that will be based on the resistance of the voltmeter and the resistance of the fixed resistor.
yeah,
So the total resistance of these two, how are they connected?
in parallel.
In parallel. So you find the parallel resistance and then find the potential difference across it. That will be read by the voltmeter.
Mm,
Hmm?
yeah. So that then it will be low, no? The voltmeter.
Calculate it and see. Tell me how much is the value. Yeah, it has to
Yeah,
be lower because why? The resistance, total resistance will be lower, isn't it?
and the lowest value of the resistance.
Total resistance of the R and V will be like less than 1000. There is a
606.
yeah. Somewhat. Now without even a calculation, you can say
Yeah. Mm,
if
so
it is like
667.
667, what is the potential difference?
Mm, how much is the LDR? LDR is 50.
200.
Then 650.
Addition. Huh?
7 or 11 100 into voltage is 4.5. And then that is 3.46. Very less.
Uh, yeah, so you can what you can say it is
Yeah.
less than 3.75. Hmm?
Um,
See how
so,
I do it. I just take the addition and I take the ratio. Yeah,
so the don't get like give a like a writing that's a calculation.
explanation. Yeah, that's a calculation. So explanation is you can write the parallel resistance is less than 1000 ohms, or therefore the potential difference across R is less than 3.75.
Um,
You can support it with the calculation. Hmm? Right. Now, we ignored the resistance of the voltmeter in part A. Now,
yeah,
we'll take the resistance of voltmeter and we'll redo the part A. Redo the
yeah,
part A. Taking the potential difference also into consideration. Like this is now how many ohms? 1 mega ohms. And this is
yeah,
1000 ohms. Taking it together and do it and find the voltmeter reading and
yeah.
compare it with the first one.
That's also almost the same. 3.7.
Yeah. So how much you get?
Three,
It's like 8.749, isn't it?
yeah, 3.7.
Uh, So now do you understand why we use a higher resistance voltmeter? Hmm?
Yeah, yeah,
Mm, right. So it's almost same, 3.749 and 3.75, which are like almost same. Hmm? Right.
yeah,
Am I clear?
yeah.
All right. So let's go back to our presentation.
There's another question.
Right. Now these are the answers. So it is like, there's another question. Yeah, we did that.
Yeah, question.
Ah, that one. That one. Yeah, that is doable. I'll just tell something on this and go. Like, see the
Ah,
accuracy, which is like 99% equal to what we got in the part A. Hmm?
yeah,
Right. Fourth one. Fourth one. Yeah, just one more. These two, right?
yeah.
First part is easy.
So the potential demand is 20, 20 over 20 into 1.2
Mm-hmm.
part B and
It's like
better
20 of 100, right? 20 of 100 into
20 over
60. Mm. 1.2, that's correct. Power
1.
dissipated in 20 ohms. Which equation is easier?
Power dissipated in the 20 ohms.
Now,
Q
do we need to
equals
find the
Q
current?
squared the R. No?
Yeah. So we don't need to find the current, right? So we also already know what is the potential difference across it. Since we
Yeah,
know the potential difference across it, we can use P equals V squared over to find it. Hmm?
V squared the R. Yes. V is the
In the previous
1.2.
one, Abhay, in
Yeah.
the previous one, make sure that you write this is more than 1 volts, huh?
Okay.
Because that's like a thing that they want us to show.
Ah,
Am I clear?
yeah.
Is the potential divider making things easier or making things difficult?
Easy. No?
No, you don't have to find currents. Hmm?
Yeah. Yeah.
Now let's move on to see how thermistor's resistance is measured over varying temperatures. Now this is like a bit of IGCSE topic. So we put it in a water bath and there is a heater. Yeah, usually you can use a Bunsen burner. So
Yeah.
the thermometer is kept close to the thermistor and we want to take a resistance reading. What we do, remove the heater and we use the stirrer to stir up and we keep the temperature constant in the water bath and we take the thermometer reading. Mm? So that's
Yeah.
how we check the temperature and resistance variation of a thermistor. So when you do that, you get a graph like this. Yeah. So it's an exponentially decaying graph. So resistance of the thermistor with the temperature like this. Yeah.
Yeah.
So sketch that on sides. Okay. Done, right?
Yeah.
Then this is how we calibrate a NTC thermistor. So calibrating NTC thermistor means the same setup. We use it to measure resistance at a different temperature. So sorry, we measure the resistance at a different temperature and we calculate, we can give out the temperature. Now, like thermostats that you have in ACs, The air
Yeah.
conditioners have thermostats, so they alter the temperature automatically. So
Yeah.
now you have like eco mode, several modes are there. So all these modes works according to the thermostat inside. So
Yeah.
thermostat's resistance is read. Accordingly, the triggering mechanism works inside the device, and like the according to that particular temperature, that output voltage or the input voltage, sorry, the input voltage to the triggering mechanism is decided. Huh?
Yeah.
All right. So that's what is meant by calibrating a NCC thermistor means. So that means for different temperatures, so different resistors values. Now the thermistor has different resistance values at different temperatures. So getting certain set of data is known as the calibration of a NTC thermistor. Okay.
Yeah.
Right now, we will look into how IV characteristics are drawn. Now, remember, the potential divider is used in, I explained there are three applications. So first one was Wheatstone bridge, second one was electric sensor circuits, third one is drawing IV characteristics of different electrical components. Remember that?
Yeah. Okay.
So now what we are going to do is we are going to see the variation of V and I of a fixed resistor. So for
Okay.
this, what we do use is a potential divider. So for this, now I remember the idea using the potential divider. What is the advantage? We can increase the potential difference across a device from 0 to its
Yeah.
maximum. That is the supply. So we
Yeah.
connect the fixed resistor like this. So when we move the slider up and down, we can change the resistance enclosed in the this particular circuit, so that when it is changed, we can change the potential difference across the device that we test. Yeah.
Yeah.
So if the slider is all the way up, what is the potential difference across this device?
That's
10,
lower. Yeah. Minimum.
maximum. Say the power supply is 10 volts. How much volts is obtained by the fixed resistor?
Minimum. Zero.
No, no, up, up, up. When it is moved up, all the way up.
So when it's moved all the way out, the
Mhm.
other resistance like the big one,
Yeah,
that one increases.
it is not what we are measuring. No. The big resistance is what we are enclosing against the fixed resistance, isn't it?
Yeah. So then voltage that what are we measuring? Voltage across fixed resistance.
This one. So when the slider is moved all the way up, what is the potential difference across this one?
That's zero, right?
Then what about this? Ah, then what about this? Ah,
Uh,
then then it's
oh,
maximum.
good, good.
Huh?
Yes, correct.
Huh?
Yeah, I forgot
Other way,
the
right?
power supply is somewhere. Yeah.
So when the slider is here, it is the minimum potential difference, isn't it?
Yeah. Yeah.
Huh? So when we move it all the way up here, it gets what?
Maximum.
The maximum. That is the power supply. Hmm? Am I
Yeah.
clear?
Yeah.
So you can also learn it like this. Now let me clarify this to you. Now you can consider this composed with two resistors. Now this white one and the orange one. When the slider is all the way up, this orange one is high. So you get all the way up to that particular length, the potential difference. If the slider is all the way down,
Minimum.
it's here like this. You get 0 volts across the this thing because this orange one is almost 0. Am I
Yeah.
clear?
Yeah.
So when we do take the readings, we take the graph of voltage against current. So voltage is the potential difference will be my independent variable. Current will be my dependent variable because I changed the potential difference across the device, and then measure the current, that is the independent variable. Now tell me, what is the gradient of this graph represent?
For a fixed
I over
resistor,
hmm?
resistor.
Is it
1 over, 1
uh,
over. Yeah.
1 over? So when I do this experiment, I get a straight line. Hmm? So what does that mean? The gradient is constant. So
Yeah.
gradient is I over V. Gradient is 1 over. That means the resistance is constant. If I want to find the resistance of the fixed resistor, I can get the reciprocal of the gradient.
Yeah.
Right. Now tell me, how do I get the negative part of the graph?
Mm, negative. Mm, mm,
How do I get the negative part of the graph? Simple. I reverse the power supply
ah,
and redo the experiment. Huh? Am I clear? Huh?
yeah. Yeah.
Ah. See, so much to think, but it's very simple. Hmm? Right. So shall we draw this down quickly
Yeah.
under fixed resistor?
That
Now,
means the circuit diagram on the graph.
yeah, circuit diagram on the left and the graph on the right, and this right up here.
Is there,
Now,
should I leave space to write anything?
just a bit of line below, because to say how you get the negative part of the graph.
Yeah.
Now, think and tell me, if you are going to draw the IV graph for a filament lamp, how I'm going to change this circuit.
Mm, so then you remove the fixed resistor and the filament line.
Simple. Didn't we discuss this earlier? Hmm? Like in the previous one where I introduced the potential divider, I showed you how it is connected through wires. Remember? Hmm?
Yeah, yeah. With the rheostat.
Rheostat, yeah. When I was introducing the rheostat to work as a variable resistor and a potential divider.
I do this now. There's something to write.
Yeah, right. To get the negative part of the graph, to get the negative part of the graph,
The negative
part of the
part of the
reverse
graph.
the power supply, reverse the power supply, and redo the experiment. Reverse the power supply and redo the experiment.
Oh,
Right. Now let's draw the thing for the bulb. Now can you try?
oh,
So we have the variable, sorry, the rheostat, the potential divider, and we have the same circuit, but replaced with what? The bulb.
okay.
Now, can you recall how the graph will look like?
Graph rate as you know that
Filament is, now I'll give you a hint. So as we increase the potential difference across the filament, potential difference is simply energy. When energy is given to the filament starts to burn and it's glowing, right? That's when
resistance
it starts.
increases.
Resistance,
It increases.
sorry,
Resistance increases.
resistance increases. What will happen to the gradient of the graph?
Gradient will reduce, it will flatten.
Increase, yeah. So this will be the graph, isn't it?
Yeah,
See, the graph's gradient reduces. That means resistance increases because the gradient is not resistance, it's 1 over R because it's I over V is the gradient.
yeah,
Hmm?
yeah.
So remember in advanced level, especially in unit 3s, if they ask a circuit diagram to be drawn for IV characteristic, that means to draw up a conclusion of how potential difference affects the current, you don't use the variable resistor to draw the circuit. What circuit diagram you should use? This.
Yes,
Why do we not use the variable resistor? We can't vary the variable resistor so that the potential difference is across the device to be zero. So we can only do that by using what?
yes.
This one, rheostat, potential divider.
Okay. Anything to write?
No, nothing to write. Hmm?
Okay.
Can I? It's the same thing like you to get the negative part of the graph, you reverse it. So it's same as the previous, no?
Yeah,
Identical, right? Huh?
yeah,
Right now, when you're doing the diode, diode has a significance compared to these devices, right? Diode does not work in both the directions. It
yeah.
works only for one
And
direction, isn't it? Hmm?
yeah,
So if you look at the diode's symbol, diode is something like this. No, the symbols actually shows us why the diode is considered to be a monodirectional device. Hmm? So we have the diode symbol like this. Yeah.
yeah.
So what does that mean? The current only passes in this
From
direction.
left to
Hmm?
right. Yeah.
So if you connect this one this way, that means in the direction of current flow, we say it as what bias? Forward bias.
Forward by.
If the connection is the other way, we call it as reverse bias. So reverse bias, it is not working. Hmm? Like current will be zero, but
Yeah.
forward bias it will conduct. Hmm? Okay, can you draw this next to the title so that you
Okay.
will recall some of what you did in the past? But when we do the IV characteristic, we draw both reverse and forward bias using the circuit. Okay,
Yeah.
right. Are we done? Can I change back to the PowerPoint?
Alright. Next to the heading, no?
Yeah, keep this area for the circuit and the graph.
Mm, reverse by. Forward by. Okay. That's it. No? Yeah.
Now let's see the circuit. Can you guess?
Right. Yes. Just I guess again just replace the diode with the diode.
Hmm. But there is a small thing that you need to consider when you're using a bulb. Sorry, the diode. When a diode is used, the only thing is diode is a sensitive device. If you have a large current, the diode can explode. Hmm? To avoid that, what we do, we have a safety resistor connected along with it, so that there will be no large currents to the diode. Hmm?
Yeah.
So it's a safety resistor. Okay.
Okay.
Right. Now let's look at the IV graph. So IV graph looks like this. So until a certain voltage is passed, until this certain voltage is passed, there will be no current. So that means the resistance of this section will be like infinite. It's like off. The diode is not working. But
Yeah.
after a certain while, the current starts increasing for increasing voltage at an increasing rate. So that means the gradient of the graph
Mm.
increases. Gradient of the graph increases means
Resistance
resistance
will be
reduces. Now this particular voltage where it starts conducting is
0.6.
it's called the knee voltage. It's like a knee. We call it as the knee voltage. So between this section, so the gradient is zero. That means the resistance is infinite. But the reverse bias region, this is quite phenomenal. In the reverse bias region, the current is like, voltage is almost zero. But after a certain while, the junction breaks. Now, this diode is made using intrinsic types of semiconductors, P type and N type semiconductors, so that you don't need to know about this breaking of the junction. So the junction breaks and the minority carrier starts to move, hmm, maybe either holes or electrons. So when the minority carrier starts to flows through, the current will be there. There will be a very high current. So we say the diode is broken. Hmm? breakdown voltage. That particular voltage where the diode breaks, we call breakdown voltage. Now we have a certain set of diodes that we use it in reverse bias mode. Hmm? Now, even if I say this diode breaks at this particular mode, it doesn't mean that we cannot use it. We do use the diode in the reverse bias mode. So such diodes are called Zener diodes, but they don't really come for your exam. They only work in the reverse bias mode. When they work in the reverse bias mode, they maintain a constant potential difference across the device. Because the circuit is because the junction is already broken. Zener diodes are usually used in like refrigerators, generators. Generators means diesel engines. They
yeah,
when they are powered up, so you need to keep a constant potential difference across it. So to do that, they have these Zener diodes. Something extra which you don't need to understand. I
yeah,
just need to mention it. Okay,
yeah,
right. So can we draw this down
right,
and leave a small line below to write about this safety resistor?
yeah,
I will just highlight the safety resistor so you would see this one, the one with yellow color.
yeah,
Right, below this diagram, right? Aware?
Yes, sir.
Right? A resistor is connected in series with the diode. A
Yes.
resistor is connected in series with the diode. A resistor is connected in series with the diode
Mhm.
to prevent to prevent to prevent large currents to prevent large currents to prevent large currents through the diode through the diode which could which could burn the diode.
So the diode
Hmm.
is now in that other in the diode in the circuit diagram, current is allowed to go from bottom to top, like from bottom to top.
Yeah,
Not electrons, no current.
because current and electrons are in opposite directions.
Yeah, so electrons can flow from top to bottom.
Yeah. So that's why the scientists did not know what the actual current was. So that's why they had like standard current and the conventional current. Huh?
Um,
Later, oddly, they realize about this. So now
um,
they can't change the standards. That's the thing, huh? Because every mathematics behind this is derived because of that very essence.
um,
So you will learn even when you go to engineering, you will learn about. You must be learning about in complex numbers. Hmm?
I, yeah.
You're doing maths, no? So you're learning complex numbers. Are you learning complex numbers?
Not yet, no,
Ah,
very welcome.
okay, so those complex numbers will be used in certain cases. So circuit theory, something called circuit theory. Right. So something extra. Hmm?
Yeah,
So shall we move on?
yeah.
Right. So we are moving on to the last parts of the section. So we are going to measure, we are going to investigate the internal resistance and the EMF of a cell. Now, when you take a battery does not always provide us the marked potential difference. It shows something lower than that. Now, say that a 1.5 volt battery, if you
Mm.
measure using a voltmeter, even a very sensitive voltmeter, you will get something close to 1.47, 1.48. Some of these potential difference will be low or lost. So that is due to the internal resistance that they are inside the battery. Huh? So now if you look at the battery has a EMF epsilon and internal resistance small r. And let's say we connect a load
Smaller,
resistance to, huh? Small r,
smaller,
small r, simple
smaller.
r. I used to call it small r. So the big R is the load resistance. So if you apply the Kirchhoff's law, so sum of all EMFs is equal to the sum of potential drops. So epsilon is equal to what? If the current, let me draw the current through the circuit. So say I current passing through this circuit. Hmm? Say there is a current I passing through the circuit. If a current I passes through the circuit, what I can say? The epsilon, that is the energy given from the battery, is dissipated through the fixed resistor, which is the load resistor, as well as the internal resistance. So what we actually use as the battery's voltage is the potential difference between these two terminals. We call it as the terminal potential difference. So terminal potential difference is the potential difference across the load resistance. So when we take the potential difference across load resistance, that is equal to what?
Yeah.
I capital R. I capital R means epsilon minus I simple r, because this particular voltage we are not using. So that's why when we measure the voltage of a battery is very much little less than what is rated. Okay.
Yeah.
Okay, so shall we draw this down on the right hand side, and shall we write down these 5 bullet points?
Okay.
Give me a second, I'll drink some water and come. You
Yeah.
draw this.
Oh, I give
All right, done.
yeah.
Okay, can I erase this part and move to the next one? Did you draw the current eye?
Yeah. So simple R is the internal resistance.
Hmm. Hmm. It's nothing but another resistance connected with this in series, isn't it?
Yeah.
So now just imagine internal resistance is huge. What can you say about the potential difference across that? It is going to be very high. Huh?
Yeah.
So is the battery is going to be useful then?
Yeah.
No, that's what happens when the battery is old, like aging. The internal resistance becomes bigger and bigger, so that the terminal potential difference becomes lower and lower. It's
Yeah.
another potential divider. Do you understand?
Yeah.
So R and simple R. Hmm?
Yeah.
Did you mark EMF, loss volts, terminal potential difference?
Yeah.
Ah, right. Now I'm going to do the experiment. So now this experiment, we have a circuit diagram. So let's look at the circuit diagram first. Don't draw, just listen. Now here, what I do is I connect the battery. Now this dash line in the box. Uh, is representing the battery with an internal resistance R and epsilon EMF. Let me draw the epsilon here, right? So there is a EMF of epsilon, and say there is a current I passing through this circuit. There's a current I, okay? So when the current I is passed and there is a variable resistor here. So why do I have a variable resistor? So I can control the current in the circuit. So I can control the current in the circuit. When I control the current, what in return change? The terminal potential difference, right? The potential difference between the two terminals of the battery. So I change the current by changing the variable resistor, and I measure the potential difference across the two terminals. So what is my independent variable going to be then?
The current.
Current, yeah. The current is my independent variable. The dependent variable that I measure is what?
Terminal PV.
Terminal PV. Right, now this is the equation, right? So epsilon I times capital R plus simple R.
Yes.
So now what I do is I subject the terminal potential difference. When I subject the terminal potential difference, I need to subtract EMF by the lost volts. That is the potential difference across the what resistance? Internal resistance. Now I can rewrite this expression. IR is measured by what? IR is measured by the voltmeter, isn't it? Voltmeter is connected across the terminals, so it is also in parallel to the resistance. So that is the terminal potential difference, V. And I rearrange this formula. So V is equal to minus R times I plus epsilon. Yeah, isn't it?
So V measures the voltage drop across the internal resistance.
Simple R, yes. I simple R. I
So the
have,
V will be a very small value.
I didn't introduce a smaller V, no?
No, like internal resistance is generally like small enough.
Huh?
So, so internal resistance is like the voltmeter measures the voltage drop across the single line.
Hmm, 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 hmm. I was expecting that. That's good you asked. How the voltmeter is connected across the variable resistor?
It's connected in parallel.
Ah, so
I
isn't
don't know
it like
what it's connected in series.
eh?
No.
Series?
No, sorry, parallel, sorry.
So by measuring the terminal potential difference, I measure the potential difference across the variable resistor, isn't it? But I need to connect it across this. Why? Ammeters we assume to have no resistance.
Yeah.
So epsilon minus I simple r is equal to I capital R. I capital R is the terminal potential difference. So I subject terminal potential difference and I rearrange this equation times as minus R times I plus epsilon. Yeah, yeah,
Okay.
see?
So then,
Huh?
then why don't you like connect the voltmeter like across the particular like shall I annotate and
Because
say
I need to have the potential difference across the terminal. So if I have a small resistance here, I would not measure it, isn't it? I would not measure
um
the terminal's potential difference. Am I
um
clear? Huh?
it will include the emitter.
Hmm. Okay. So what is my y variable? So my y-axis will be the terminal potential difference. Current axis will be the ammeter reading, that is x-axis. So if I draw a graph, so the negative gradient of my graph will give me what? The internal resistance, and the EMF of the graph will give me what? The EMF. Isn't it? Yeah, shall we write it down? So I write it here. Radiant, sorry, internal resistance equals negative negative gradient, huh? Then EMF is equal to what? Intercept. Intercept on the EPD axis.
What do you call that thing? What you say name is silent
Epsilon.
lecture?
Epsilon.
Epsilon.
Epsilon. Epsilon. Some people call it epsilon. It's like E. Simple E in like Greek.
Yeah.
You usually use it for universal set, right? In set theory.
Yeah. Ah, yeah. That
Epsilon.
one, you know, the label on the battery is let's say 1.5 volts. That
Hmm?
one is that simple will actually be 1.48 like that.
I didn't hear anything.
Uh, let's say the battery is labeled as 1.5 volts.
Hmm?
That simple will be 1.48 like that.
There is no
Simple.
simple V, no? Where did
The
I
simple
put a
will
simple
E.
V?
So that epsilon or epsilon.
Epsilon will be 1.5, but when we measure the V, will be less than 1.5.
Ah, okay. Ah,
Okay?
okay.
It's not the marked value. Am I clear?
Yeah.
So when we measure the two ends connected across a voltmeter, we don't get the marked value. That's why we say some potential difference is lost or volts is lost. Like energy has been dissipated to the internal resistance.
Yeah.
Always connect the voltmeter across the terminals of the battery. Huh?
Yeah.
Now you have a set of data below your note. You should draw the graph and find the internal resistance and EMF. Huh?
Yeah.
We'll do it next time also. But you do it at home. Huh?
Yeah.
After you draw this, we will see how it is done. Hmm?
Yeah.
I have a small video for that. Now, usually when we do this experiment, the same set of data are used to another experiment. Hmm? That is
Ah,
what we have to learn at the end. The maximum power, internal resistance, and load resistance relationship. Hmm? So now when we do this experiment, we know the potential difference and current through the circuits, right?
yeah.
So we take the power output of the variable resistance, external resistance. So then we draw it against the power output. We draw against the external resistance. So at a certain value, the power output becomes maximum for a
Yeah.
certain variable resistor value, and then we compare that, and we can. I will show you that the when the power output becomes maximum, that this external resistance equals to the internal resistance.
Yeah.
Using differentiation, you can prove that, but you don't have differentiation there. I just wanted you to do the graph and identify that. Hmm?
Yeah.
Once you're done, let me know.
Yeah.
So make sure that you write negative gradient. Huh? Otherwise, it's just the gradient gives you minus R. Hmm?
Yeah.
Right, done?
Yeah.
Did you write the internal resistance is negative gradient, EMF is the intercept on the TPD axis or y-axis?
Yeah.
Yeah. Okay. Right, now let's look at this experiment. Right. So watch it.
Hi, this is Mr. Reese from.
Can you hear?
Yes. Yeah.
Okay, so you mute your microphone from your end, so it will be faster. Okay.
Yeah.
Hi, this is Mr. Reese from Malmesbury Science, and I'm going to show you how to do the A-level physics practical, how to find the EMF and internal resistance of a battery. So batteries provide an EMF, that's electromotive force. You can think of that as the total voltage that the battery can output. However, batteries are not perfect conductors, so they have a little bit of resistance inside of them. So we can model a battery as a perfect battery with a little resistor inside as well, and we're going to call that the internal resistance. What we want to do is hook up a battery to just a load resistor, and it's a good idea to have a variable resistor so you can change it, because we want to change the current flowing through the circuit, and therefore the current flowing through the battery. We want an ammeter in series with the battery and resistor as well. So what I'm going to do is change the load resistance. So this is my load resistance here. You might have some different looking variable resistors, but it's going to be the same setup. And I'm going to get my current to exactly 0.10 amps. And there you go, fairly precise. So now that I have my current, I then want to measure the terminal PD. Now the terminal PD is the voltage.
Yes.
This video and audio, they are not like going together. Like the audio is fast, the video is lagging.
Wait, I will share it again. So mute your end and tell me if it is going together now.
Yeah.
How to find the EMF battery can out. However, batteries are not perfect conductors.
Now?
I can't
How is
see
it?
the screen. No, I can hear the audio, but can't see the screen. It says has started screen sharing, can't see the screen.
Wait. Can you see it now?
I can see like small text saying Saman Aravinda has started screen sharing.
Can you see my PowerPoint at least?
I can only see like the gray thing with that message has started screen sharing.
You leave the meeting and join again.
Okay.
Wait, I will put you into the waiting room. Can you see the PowerPoint now?
It's loading. I don't know, it says it's that gray screen, it's saying Saman Aravinda has started screen sharing.
I don't know. The internet is fine.
Today is the 29th. Oh?
Okay, now? Now?
No, still it's that same thing. Is today the 29th? I think so.
30th.
30th. I don't know again. Internet. Your
Your
internet
data
is
might
okay.
be.
Huh?
Yeah. My internet is fine.
Shall I leave and join again?
Mm-hmm.
Sir?
Yeah, yeah.
I'll leave and join again.
Yeah. Okay, can you see the shared screen now?
No. Shall I send you a photo of what I'm seeing?
No need. You can at least hear. You can
I
hear what
can,
I say.
I can hear. Yeah.
Then we'll do it. I'll send you the link. So try to see the link and look at the experiment. Huh?
Yeah.
Did you receive the link?
Yeah.
Hi, this is Mr. Reese from Malmesbury Science, and I'm going to show you how to do the A-level physics practical, how to find the EMF.
Shall I watch it?
Can you see my screen now? At least you can't see the screen now, even.
Did you start? It says someone Aravinda has started screen sharing.
Have you stopped the incoming video?
No, I didn't do it.
Did you do something? Let this is how I usually do share the screen. You can't see my presentation.
Now
Even.
can see. Now can see. Now can see.
Okay, watch it on this, huh? So it's easy for me to explain. Huh?
Yeah.
Hi, this is Mr. Reese from Malmesbury Science.
Oops, sorry. Did you hear it properly?
Yeah, I heard it. Yeah.
Hi, this is Mr. Reese from Malmesbury Science, and I'm going to show you how to do the A-level physics practical, how to find the EMF and internal resistance of a battery. So batteries provide an EMF, that's electromotive force. You can think of that as the total voltage that the battery can output. However,
Video, I can't it's not syncing.
It's your internet connection, Bear, I think, because
Mm,
previously I did the same and like it was going well. Anyway, I will play like in low quality now. See if it is now. See how
batteries are
is it
not
can
now?
perfect conductors, so they have a little.
like it's
Okay, never mind. Can you see the video? Like when I pause it, can you see the screen?
yeah, I can see the video, but it's like lagging. Like it's not. Yeah, I can see it. It's
Okay, you
lagging.
watch it later. Huh? So we will
Yeah.
from I think your internet connection is very slow. So you draw the two graphs at home and we will discuss it next day. Huh?
So two
Okay.
graphs.
All right.
What are the two
One
graphs?
for the internal resistance, one for the internal resistance, and one for the power output. This one.
Power
I will
output.
do that theory quickly then. Can you see? Can you see my screen?
I can see that video, the Mars Belly video.
Now you can't see anything. Like my what I am sharing now, you can't.
I can see that man, that white man with that thing.
Right. So it's your internet connection is very weak. So seems to be either you increase it with data and can you upload it some data? No,
Uh,
you can't.
I can tell it might take some time. Uh,
Right. Anyway, so we will do it next time then. Draw the internal resistance graph that you know
yeah,
that. So I
yeah,
will discuss that one next time. Okay. All right.
yeah.
Okay. See you.
Should I
Bye.
like
Take care.
keep anything for the next day? Like we finish this in 2 minutes for the next day?
No, no. We do the all the other questions in the tute. We will discuss all the questions. Hmm?
Right. Yeah.
Entire the questions which are remaining, we'll do. We'll finish after that. Current
Yeah.
section. Hmm?
So I
Okay.
have to draw the graph
Okay.
and do the question.
Yeah. Graph and the remaining questions. Yeah. In the tute. Hmm?
Ah,
Okay.
okay.
And then we'll discuss the difficult ones. Okay.
Okay.